So I've seen the ideal gas equation. So the ideal gas equation is PV equal to ideal gas equations we have seen. So let us see how true are these ideal gases. So ideal gas equation states that PV is equal to nRT. While deriving this relation, we have made some assumptions. Assumptions that we did. Assumptions what is being considered during for deriving this PV equals to nRT is this. Number one is that size of the gas molecules is negligible, identical, spherical. Number two, there is no force of attraction. No force of means gravitational force between them is not present. No force of attraction exists among them. These are the two assumptions, but in reality, no real or actual gas shows the above assumptions. So the real gas, so the behavior of real gas deviates from the ideal gas, is different from the ideal gas, from the ideal gas. Let us see how differ is it. At low temperature and high pressure, the above assumptions are valid to certain extents. The above assumptions are valid to certain extent, but not at some other temperature or pressure. Okay? Example: hydrogen, oxygen, nitrogen, they do behave like real gases, like ideal gases at high temperature and low pressure. At low pressure and high temperature. What did you write? Sorry. I wrote here long. At low pressure and high temperatures. What did I write? At low pressure and high temperature. I'll show you. Okay, the above assumptions are valid to certain extent. Example: they behave like ideal gases at low P, low P and high T. So if you plot, if we see the behavior, as we know, so PV is equal to A naught T. So if we take PV by NT is equal to R, and what is the value of R? R is 8.314, which is a constant. So if we plot a curve, you see this line represent the constant R, this is R, and if we see all other gases, different gases, if you compare them at different temperature, you see as temperature increases, if you look from as temperature increases, R will decrease. T increases means R decreases, right? So as the temperature increases, you will see the graph will fall. The graph shows some different behavior. It is very something like this. This is at T1. Now increase the temperature even more, the deviation is even large. Deviation will be even more large. At even high temperature, this is even large. Actually these two will a different value, no problem. You can show this one like this also. I'll show you. It's better to so the curve will be something like this. So at different temperature, even that means they show different thing. You could have drawn a little bit here and also no problem. So this is how it is changing. This is T1, this is T2, this is T3. So T1 greater than T2 greater than T3 at different constant temperature. As the temperature increases, we can see that it is deviating out. So this is R. This is the value of R, which is 8.3. Or you can also write this as PV. This is PV by NT, and this is different pressure. So as you can see, is the pressure increase at low pressure. If the pressure is low, and the temperature is then at the low pressure and the temperature is high, we can see that at low pressure and high temperature, we can see the graph is almost a straight line. That means if this is T0, let's say, so definitely T0 is greater than T1 greater than T2 greater than T. So at very high temperature and low pressure, you will see it is the gas. Think about it. Now this is the figure one. So think about it at high temperature, low pressure means pressure is very low. That means if you are looking at the container, keep the container open. Keep the container. If this is your container here, the container is not been tightened, so that means the amount of gas that is present, the volume of gas that is present in the container, for that particular volume of the gas molecule, there are lots of space to move around. However, it is being heated. As it has been heated, that means it is at a very high temperature. It is at quite a large temperature. It is. As it is a large temperature, high temperature, so the gases inside, they are moving around very fast. So their motion is very random. They're moving out in every direction. Got it? So as a result, what do we see? Very little amount of molecule is present inside the container. Not very lots of molecules are not present, so they are free to roam around in there. So in this particular condition, we will say that the gas molecule, whether it's an oxygen, it may be an oxygen, O2, or nitrogen that is present inside the gas, it will behave like an ideal gas. It will behave like an ideal gas. That means when it behaves like an ideal gas, what do we know? That if you increase the pressure, temperature, volume, all are according to the curve. Whatever Charles' law said, Boyle's law says, Gay-Lussac's law says, they all obey accordingly. Now, for other curves, just look into the other curves. So if you look into look at the Boyle's law curve. So Boyle's law is between. So if you look at the Boyle's law, so Boyle's law says that pressure and volume are inversely proportional. That means, as we have seen, we have drawn this curve here, right? So their exact ideal gas will follow P is inversely proportional to V. All inversely proportional curves are like this. So ideal gas is like that. So ideal gas will follow like this. But then this is ideal. They do not exactly follow. So then if it is not an ideal, for the real gas, it would be little different. So for the real gas, it would be somewhere here and there. So real gas will be close to it, but not exactly according to it. Sorry, it should not touch the curve. Even more, as we increase the temperature, you see P is inversely proportional to V. P is inversely proportional, T being the constant. So this is one particular temperature. So at different temp, P is directly proportional to temperature. So as the temperature increases, you'll see the curve will become even more. The curve will become even more sharp. It will become even more sharp like this. Again, it is not touching the, we'll go from here. Okay. So these are different temperature. So this one is the ideal. These are real gases. Real gases at, this is at T1, this one is at T2. Now T1 being greater than T2. So what do we know? At low pressure, high temperature, it is more ideal gas, right? So a real gas will behave like oxygen, nitrogen, hydrogen. They will behave like a real gas at high temperature and low pressure. So definitely T1. Look at the T1 curve. T1 curve is almost close to the actual curve. Theoretically what it should be. But as the temperature decreases, it becomes more and more become a rectangular hyperbole. The sharpness increases. Okay. So finally one more curve. The Charles law. So this was the Boyle's law curve. Now look at the Charles law. So Charles law gives the relation between volume and temperature. So we know V is equal to V naught plus V naught T by 273.15. Right? You can see it is like a straight line. That is, we have also proved earlier that V is directly proportional to temperature. So that is the directly proportional curve. That means it should follow. The ideal gas is like this. It should be going straight. Okay, it should be going straight. I'm not taking 0 Kelvin, so it is going straight. So here this point is 0. This is the temperature, this is being the volume. But the real gas, definitely they will not follow. So again, at high temperature, real gas behaves like an ideal gas. That means the curve is quite a straight line at the high temperature, but it deviates out as the temperature falls. I should draw even more little bit properly. So let me use the blue one. So you see, here the temperature is very high. In these cases is high. So at high temperature, it is more of a straight line. But at low temperature, it is not. It is moving away. Similarly, if this is some other one, this is the ideal gas of some other P2. So this is at particular pressure 1 constant. This is another gas. This is the TV curve for the ideal gas at some other pressure P2. Then here also at high temperature the curve will be shifting out. At low temperature again it will be, but at high temperature it is a straight line. So I hope you understand, because this thing you do not memorize it, know it. All the time you see, as the temperature is high, the curve is whatever curve we use, it will be always, this is volume, this is pressure. This is from Charles' law, this is from Boyle's law. So we see, as the temperature is always high, the curve will be always very close. The PV curve or TV curve will be very close to the theoretical curve for the gas, but at this temperature is low, they deviate out. Okay, so high pressure, high temperature, low pressure, gases like oxygen, nitrogen, they behave like a real gas. This is the summarization of, so you need to remember this. At high temperature and at low pressure, real gases, ideal gases, real gases behaves like ideal gases. Okay, so let's proceed. Now let us come to the main assumptions of kinetic theory of gases. Kinetic theory of gases. What are the assumptions? So, if you look at the container, let us look at container for understanding purpose. This container contains a real gas at low pressure and high temperature. That means it is almost close to almost like an ideal, it is like an ideal gas in the ideal environment. It is believed, the assumptions what we consider for the gas molecules are called the assumptions of kinetic theory of gases. Based on this, whenever we are going into molecular scale, we are going to always apply this principle to do our maths, to solve problems, to deduce new relations, considering this, the ideal gas behavior. Though later on in higher physics these things changes with quantum mechanics, But in classical mechanics, we go with the kinetic theory of gases. So let us see what are the assumptions of kinetic theory gases. So assumptions of kinetic theory of gases states. So assumptions of kinetic theory of gases. Number 1, all gases consist of molecules that are rigid, spherical, identical, in every respect for a given gas, and different for different gases. First assumption. So we considered all the molecules are spherical, like a spherical glass marbles. They are identical in shape. So for one particular gas, they are all identical. For other gas, it is different. So maybe this is oxygen, this is nitrogen. So this sphere is maybe a little big. However, within the gas, they are all identical. Number 2, size of the molecules. Size of the molecules are negligible. Size of the molecules are negligible compared to the distance, compared to the large distance between them. Number 3, molecules are in a state of continuous random motion. Molecules are in a state of continuous random motion in all possible directions. So if this is one molecule, it is going like this, going this way. There is no specific direction in which they are going. They can go in any direction. They can go like this. And what these things are, here it has undergone a collision. At this point they have collided with the other molecules and also with the walls of the container. So they are moving in all possible directions. I'll show you the arrow to explain this. Okay, molecules are in a state of continuous random motion in all possible direction. During this random motion, they are not only colliding with each other, but also with the walls of the container. Walls of the container, which I have already shown you earlier. So this is our container. The molecules are, I'm showing a little big. It is not only colliding with another molecule and then coming this side, it is also colliding with other molecule with the walls of the container. all the walls. So like this, one may be colliding with the top, and so on. All possible direction they are traveling. The collisions are perfectly elastic. Are perfectly elastic. Perfectly elastic means momentum and kinetic energy is conserved. Between successive collision, the average distance covered by the molecules is called mean free path. What does this mean? This is one molecule. It went like this, collided with this molecule, and then again traveled a little bit of straight distance and collided with another molecule, and then it went this side and collided with another molecule. So if you take all this distance, lambda 1, lambda 2, lambda 3 and so on, then this average distance lambda n is called lambda 1, lambda 2 and so on plus lambda n by n. This distance is called average or mean free path. Similarly, the time spent, the average time spent, also the average time spent between successive collisions is called relaxation time. Tau. We denote again tau, Greek letter tau, tau 1, tau 2, tau n by n. Again this is mean. All these are mean. Okay, 6. Collisions are instantaneous. This is an optional point. It is evident that it is always instantaneous. Number 8. Density of the gas remains constant throughout this motion. Nothing happened to the density because the particles are considered size of the particles are negligible compared to the vast distances between them. So these are the most important assumptions. You can say in short the main assumptions are that all gas consists of molecules that are rigid, spherical, identical and alike, similar in every respect. Size of them is negligible compared to the vast distance between them. This is the second important point. They are continuously random motion. This is the third point. They are not only colliding with each other but also the walls of the container. That is the fourth point. And then collisions are perfectly elastic. The time spent is between the average time spent is called the mean free path, and the average distance covered is called the relaxation time, and the average distance covered is called the mean free path. These are the assumptions. Let's see what we can do with these assumptions now. On the basis of kinetic theory of gases, let us see expression of pressure. Expression for pressure of a gas based on kinetic theory of gases. Kinetic theory of gases. Let's see. So let us apply these assumptions to the kinetic theory of gases. Let us consider Let us consider a cubic section, a cubic volume, in which we consider few gas molecules. This is a cubic container in which the gas is present. So, imagine this is one molecule. This molecule is under random motion in all possible directions. So, imagine this molecule is going towards this wall. So, it will hit the wall with some velocity v. So, it is in 3D. The molecule is in a three-dimensional space. As it is a three-dimensional space, if I draw the coordinate axis here, I can see its coordinate point is velocity at this point is Vx, Vy and Vz. This molecule, after colliding with the wall, it will bounce back. As it bounces back, the collisions are perfectly elastic. So the coordinate of the point at this point will be minus Vx, minus Vy, minus Vz. Correct? So we start like this. Consider an ideal gas. An ideal gas enclosed in a cubical container the gas molecules are at random motions, are continuously at random motion. At random motion according to kinetic theory of gases. Let n equals to number of molecules per unit volume. Per unit volume. So we are talking about density here. So n is n by v. Also m equal to mass of each molecule. Okay, a molecule having velocity v vector, which is v is vx plus vy plus vz, hits the wall and rebound back and rebound with velocity minus v minus vx minus vy minus vz, as the collision is perfectly elastic. So change in momentum would be, if you are considering only keeping Vy Vz equals to 0, so minus mvx and minus mvy, because the particle is going straight, hitting the wall and again returning back along the same path. So that means this is mvx and this is minus mvx. So that means my change in momentum will be minus 2 mvx. So what we are considering? Assuming Vy 0, Vz 0, just for our assumption, to keep it simple, although it is not. Then, so number of molecules hitting the wall. So if A is the cross-sectional area, number of molecules hitting the wall of area A will be half into, so we know what, how much it would be the area into, so the area will be how much volume is it traveling, how much volume is it going. So we can see like this. So if this is the area, so in time t, all the molecules which will be present in this green volume, they are going to hit. And how much distance are they traveling? So this is area, this section area is A, and this is x. So this is the volume it is traveling into, so this is the volume, right? So how much is it traveling in time t with Vx velocity? So x would be Vx into delta t, or t, simple, Vx into t. So how many molecules are traveling? Because you see, in this molecule, there will be some molecules which are returning back and some molecules which will be going. So let's see what we can do with that. So then, so this much Vx into delta t, so how much volume is going? So volume of molecules which are going would be, V would be area into delta t. So how much molecules? We know N is equals to number of molecules per unit volume. So N must be, so number of molecules hitting the wall of area A, I am going towards that, I am just showing you the side derivation here, would be N into V. And how much is this V? This is Vx, N into Vx into delta t. This is the number of molecules, but wait, out of this half particles is going and half particle is returning. So we must divide. So number of molecules that are hitting would be N by 2. So that means N Vx delta t by 2. So we can write here half area, sorry, oh yes, I missed the term area here, AVX, area also. So A Vx into delta t by 2 and small n. So this is the number of molecules that is hitting. So total momentum, so this is a side note for you. So total momentum transferred, so delta p, this is the one. So total momentum transfer would be total momentum transferred to the wall by, I'll write this as N, by N molecules. Let us write this as N dash, because N is the total. So by N dash molecules, so N dash would be, so momentum would be, sorry, So total change in momentum P would be n dash into this P. Looking at this P dash, n dash into delta P. So this delta P is how much? Minus 2m delta Vx. Or 2m. Just this is giving me the sign. Magnitude would be, so magnitude of this one will be 2m Vx. So let me clean it. Okay. So if this one's magnitude 2m Vx. So n dash into 2m Vx. But what is n dash? Let us go to the next page. So delta P dash should be 2m Vx into half of a Vx delta t into n, right? So then what do I see? Delta P dash by delta t will give me 2 get cancelled, and then m is there, Vx square, it will give me n m Vx square into area. Pressure exerted, capital P will be force per unit area. Force by area. Isn't this the force? This is force. This is the pressure. So n m Vx square into A by A. So A get cancelled. I get pressure to be n m Vx square. This is the pressure exerted only along x. Therefore, as the molecules has different velocities. Now I am considering, this is only for your assumption. Remember, this is not true. You can just take this option to understand only this part. But here we are going to apply it. So as the molecules has different velocities at different direction, so mean velocity, so this one P, so total pressure must be equal to n m v mean. V mean square. We can write this as we can write like this, Vx square mean. Yeah, Vx square mean. But for our assumption purpose, again for the molecule velocities, let's say the molecules, okay, let's do like this. Let the gas be isotropic. Then, so let us say like this. Let all the velocities are equal. Vy, Vz are roughly equal only. Then what do I get the mean? So Vx square mean will be equal to Vy square mean equal to Vz square mean. Right? All the means we are considering to be same. With these assumptions, then our V mean would be, actually V mean is Vx square, Vy square plus Vz square by 3. Now all of them we are considering to be, let's say, equal. So then this gives me V square 1 by 3, let's say all of them coming to be equal. I am not taking this as 3. Here we mean to say that the as they're equally distributed, so we can say that the mean of all this, let's say, is this. Half 1 by 3 V mean square. These are just assumptions. Just assumptions here. Where mean is where we're considering this to be as mean square velocity. You can, okay, I think I should do like this. Wait. So we're taking this all to be equal. So if all to be equal, then what can we write? V mean square would be equal to V x square Vy square mean plus Vz square mean. Okay, then this, as they are equal, so we can write this as 3 Vx square mean. So that means Vx square mean would be 1 by 3 V mean square. This is better to understand, where V mean square is equal to mean square velocity of the molecules. Therefore, we can write pressure is equal to m into n 1 by 3 V mean square. Rearranging, P equals to 1 by 3 mn V mean square. What I am writing? 1 by 3 n into m V mean square. Now density of the gas, density rho would be mass by volume. Mass, if m is the, okay, by the way, sorry, we should write this as total mass. M by V, m equals to total mass of the gas. Total mass of the gas, which you can write as n, then n into m per, what is, so here one more thing, let us go step by step. So if m is the mass of the volume, then, and V equals to 1, so if I write rho equals to then n into small m by V. So if volume is 1 unit, if V equals to 1 unit, definitely cc, therefore rho would be equals to n into m. Therefore pressure would be equals to 1 by 3 rho V mean square. This is the pressure exerted. This is the pressure exerted by a gas according to kinetic theory of gases. From this gas, this pressure is equally transmitted in all direction. Pascal's law. Then, so what we can do with this? From this, we can also come up to the expression for kinetic energy. So P equals to 1 by 3 rho V mean square. Therefore, mass per unit volume, so kinetic energy, we know kinetic energy will be equals to half m V square. Okay, mass per unit volume would be, so we know rho equals to mass per unit volume. So we can write m is equal to rho into V. Again, taking V equals to as 1 unit, 1, then we can write rho is equals to m. If rho equals to m, we can plug in there. So kinetic energy would be equals to 1 by 2 rho V square. Okay, so, or E equals to 1 by 2 rho V mean square. I'm just going to write here V now, from now on try to understand it's a V mean only. Therefore, this is 1, this is 2. If we take the ratio P by E, the relation stands between them is 1 by 3 rho v square by 1 by 2 rho v square. Please try to understand, is a mean square velocity. So it gives me rho get cancelled. So P pressure is equals to 2 by 3 E. 2 by 3 E. Pressure is equal to 2 by 3 into E. This is the pressure. This is the pressure relation between pressure and kinetic energy of the molecules of the gas.